Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the overdamped, critically damped, and underdamped cases for the source-free parallel RLC circuit, where in my previous video we solved for the natural response of the voltage in this parallel RLC circuit, V of t, where in this video we're going to label this system based on this alpha and omega naught, where this alpha was my damping factor and the omega naught was the resonant frequency or the undamped natural frequency. So we say that if alpha is greater than omega naught, my system is going to be overdamped. And this is my first case. In my second case, if alpha is equals to omega naught, the system is therefore critically damped. And the third case is if alpha is less than omega naught, the system is underdamped. Before we move on to all these three cases, recall that this alpha, or again, my damping factor, is equated to 1 over 2RC for the source-free parallel RLC circuit, and omega naught was equated to 1 over the square root of LC. If you need a refresher on this topic, I will post a link to the previous video, which talks about this in the top right-hand side corner of this video. Okay, the first case we consider is the overdamped case. And for this case, we say that this alpha is greater than omega naught. And so what we want to do is write some equations and graphs for this natural response of this voltage V of t for the overdamped case. And before we do that, I want to make a note that if we have an overdamped case, we say that 1 over 2RC is greater than 1 over the square root of LC. As a result, the square root of LC is greater than 2RC. Therefore, L is greater than 4R squared C. This L, or this inductance, is what you call the critical inductance. And the reason why we care about this is because if the inductance is greater than this 4R squared C, we will prove that it is non-oscillating, versus when it's 4R squared C, it is going to be oscillating. All right, from the previous video, we said that this VT is equated to A1e to the S1t plus A2e to the S2t. And again, just to write it out clearly, this is A1e to the minus 1 over 2RC plus the square root of 1 over 2RC squared minus 1 over LC times T plus A2e to the minus 1 over 2RC minus the square root of 1 over 2RC squared minus 1 over LC times T. Where again, this here is this S1 and this here is this S2. And based on this criterion here, we say that since 1 over 2RC is greater than 1 over the square root of LC, that means that 1 over 2RC squared is also greater than 1 over LC. I hope this makes sense. Therefore, we can say that S1 and S2 are both negative and in the real number domain. Again, just to be explicit, this here underneath my square root is 1 over 2RC squared minus 1 over LC. And since this is bigger than this will never be a negative value. All right, so we're not going to get any imaginary or square root of negative ones, making it imaginary. So that proves that it's always going to be real. And this first term here, this alpha, makes it to always be a negative value here. I hope this makes sense. So I can go ahead and say that, therefore, V of t is going to be equated to A1 e to the S1t plus A2 e to the S2t. And if I go ahead and grab this, so here we have V of t and here we have t. And if we consider that the initial voltage across my capacitor V of 0 minus is equated to 0, so that means that there's no voltage across my capacitor here until t is equals to 0. And as soon as you disconnect that source, the voltage is going to shoot up and then eventually die down due to that resistor as t goes to infinity. And what we can say is that the function as it dies down is this e to the st function. For this case, a couple of things we can note is that energy dissipates through the resistor. And we talked about this in the previous video, but it dissipates through the resistor as heat. And for this case, we say that the resistor value is low. All right, because remember in that parallel circuit, if this resistor here is a low resistance, current is going to want to dissipate through it in this direction. And lastly, a couple of examples which you can visualize is when a flashlight is draining, it goes from being extremely bright to maybe being like a medium brightness to being very low. It takes its time as it's draining. It's not instant. Another example, which is more on a larger scale, is an emergency door. And most emergency doors, when you close them, they don't shut right away. They take their time before they dissipate all their energy and then close. And that's more of a mechanical system that is an overdamped case. If you have any questions on this slide, please leave them down in the comment section below and I'll be sure to get back to you. Let's now go to the second case, which is the critically damped case, and see if we can write some equations for V of t and graph it as well. All right, for the critically damped case, which is the case where alpha is equated to omega naught, we say that to find our critical inductance, we say that alpha, which is 1 over 2RC, is equated to 1 over the square root of LC. Here we have that the square root of LC is equated to 2RC. And lastly, my critical inductance, L, is equated to 4R squared C. Next, we know that S1 and S2 are equated to this minus alpha plus a minus square root of alpha squared omega naught squared. And what I can say is that since alpha is equals to omega naught, this term under my square root is equated to 0. So therefore, S1 and S2 are equated to minus alpha, which is basically just 1 over 2RC. And now we can say that V of t is equated to A1 e to the minus alpha t, because S1 is minus alpha, plus A2 e to the minus alpha t, which is equated to A1 plus A2, and pull out this e to the minus alpha t. And since these two are just constants, we can combine them to just give us one constant, which we call A3 e to the minus alpha t. So now we say that this is the wrong answer simply because the two initial conditions, which were the voltage across my capacitor at time equals to 0 and its derivative, so VC prime of 0, cannot be satisfied with the single constant A3. And we say that we clearly did something wrong. And that's because our assumptions of an exponential solution is incorrect for the special case of a critically damped system. And again, just to be clear and explicit, there are two initial conditions which we care about in this system, which is the initial voltage through my capacitor. And this VC prime of 0 was derived from the initial current across my inductor, all right, which we call capital IO. In order to find out what we did wrong, we need to go back to equation number 4, which I'll write again. But again, this was a second order ODE, which said that d squared V over dt plus 1 over RC dV over dt plus 1 over LCV is equated to 0. Again, just to be clear, V is equals to VT, which is also equals to the voltage across my capacitor. And what I can say is that this is d squared V over dt plus 1 over RC is 2 alpha dV over dt plus, so this is just alpha again, times V, which is equated to 0. All right, in order to solve this second order ODE, let's go ahead and separate this middle term here and rewrite the equation. So I get d squared V over dt plus alpha dV over dt plus alpha dV over dt plus alpha squared V is equated to 0. Something I forgot to mention, which I'll do in editing, is there's a squared here, here, and here. And in these two terms here, let me go ahead and pull out a d over dt. And so I'm left with a dV over dt plus alpha V plus, in these two terms here, let me go ahead and pull out an alpha. And in this case, I'm left with a dV over dt plus alpha V again is equated to 0. Let me go ahead and call this equation number 1 for this video. What you're going to notice is that this term here and this term here are the same term. And I'm going to say that let's have a function f, which is equated to dV over dt plus alpha V. And let's call this equation number 2. So now if we plug in this f, or this equation number 2, into my equation number 1, I simply get an equation number 1 that becomes df over dt plus alpha f is equated to 0. And this here we like because it's a first order ODE. And again, for first order ODEs, which I won't prove in this video, we know that the solution for f is equated to this a1e to the minus alpha t. All right, let me go ahead and scroll down here while still keeping some of our previous work on the page. And I can say that f is equated to this a1e to the minus alpha t, and it's also equals to this equation number 2. So to continue, let me say that f is equated to a1e to the minus alpha t, which is equated to dV over dt plus alpha V. If I go ahead and multiply both sides by 1 over e to the minus alpha t, I'm going to get that a1 is equated to e to the alpha t dV over dt plus e to the alpha t times alpha V. I hope this makes sense how we distributed this 1 over e to the minus alpha t. And what we will notice is that this here is a product rule of considering this e to the alpha t and vt. Let me go ahead and prove this so there's no ambiguity. So if I take the derivative d over dt of e to the alpha t times v, the product rule says that I leave my first term alone, so e to the alpha t, but I take the derivative of my second term, dv over dt, plus I take the derivative of my first term, e to the alpha t times alpha, and I leave my second term alone, v. As you can see, this here is equated to a1, right? This entire thing is equated to this entire thing. So I hope this makes sense. And the reason why we care about this is because we can say now that a1 is equals to this function here. So if we rewrite it, we can say that a1 is equated to d over dt of e alpha t times v. And so what we can do is take an indefinite integral on both sides in terms of dt. So do this. This dt cancels out with this dt. My integral, which is an antiderivative, cancels out with the derivative. And the indefinite integral of a constant a1 is simply a1 times t plus c, or a constant, let's just call it a2. So then this is equated to e to the alpha t times v. the goal of this case is to find v of t here. So I can say then that v of t, again, which is equated to v, is equated to this a2 plus a1t times e to the minus alpha t. And this here is my final solution because it satisfies two initial conditions: the initial voltage across my capacitor and the initial current across my inductor. Okay, in terms of graphing this v of t, so we have v of t here and we have t here. I like to go ahead and just map out this function, or this decaying function, call this e to the minus alpha t. If we take that, the initial voltage v of 0 across my capacitor is equated to 0. So before 0, it's 0 here. So t is equals to 0. In this case, what's going to happen is it's going to shoot up and it's going to come right down faster than my overdamped case as t goes to infinity. And some things to note here is that there's little to no oscillation. And in this case, the energy dissipates as fast as possible through my resistor R. When you're dealing with systems in the real world, this here is what we call the just right case, because it returns to the original spot as fast as possible without any bouncing or even bouncing once. And some examples of this is in your EE courses, in your lab, if you have a voltmeter, right, with a meter in it, once you measure the voltage, it shoots up right away to whatever voltage you get. So it's immediate. There's no delay. Another example is, let's say, a kitchen scale. When you put food on a kitchen scale, the kg or pounds or ounces, whatever you're measuring, shoots exactly to that measurement as fast as possible without any delay. And then more of a mechanical example, which I'll write up here, is a mouse click. So when you click your mouse, it returns to the original position as fast as possible without any delay. I hope this case makes sense. And if you have any questions or concerns, please leave them down in the comment section below and I'll be sure to get back to you. So now let's go ahead and dive into the last case, which is the underdamped case. All right, for the underdamped case, the criterion says that alpha is less than omega naught. And let's go ahead and find that critical inductance. So 1 over 2RC is less than 1 over the square root of LC. So then we get that this is the square root of LC is less than 2RC. So then L is less than 4R squared C. If we remember in the beginning of the video, we said that whether L is less than or greater than 4R squared C determines if we have this underdamped case or this overdamped case. As a result, that's why we consider it to be critical. So in this case, S1 and S2, we say is this minus alpha plus or minus the square root of alpha squared minus omega naught squared. But I kind of want to write it in a different format. I'm going to write it as minus alpha plus or minus the square root of minus omega naught squared minus alpha squared. I hope this makes sense how this is equated to this. All right, so if we continue, we can say this is equated to minus alpha plus or minus the square root of -1 times the square root of omega naught squared minus alpha squared, where this here is denoted as omega d, or the damping natural frequency. And obviously the square root of -1 is j. So then we get that this is equated to minus alpha plus or minus j omega d. All right, so therefore we can go ahead and write this v of t is equated to a1e. S1 I'm going to say is minus alpha plus j omega d times t. And then we get a plus a2e. S2 is going to be this minus alpha minus j omega d times t. I hope this makes sense. Let me go ahead and pull out this e to the minus alpha in both these terms. So then I get that this is equated to e to the minus alpha t times a1e to the j omega dt plus a2e to the minus j omega dt. If we go ahead and recall Euler's identity, which says that if I have an e to the j theta, this is going to be equated to cosine theta plus j sine theta. And if I have an e to the minus j theta, this is equated to cosine theta minus j sine theta. Let me go ahead and use this identity in this term and this term here. So it becomes a bit long here, but Vt is going to be equated to this e to the minus alpha t times a1 times cosine omega dt plus j sine omega dt. I'm going to write the second term on the bottom here to give myself more room. So plus a2 times cosine omega dt minus j sine omega dt. If we keep going, this is equated to e to the minus alpha t times, let me isolate this term cosine omega dt from here and here. So I'm actually going to be left with a1 plus a2 times cosine omega dt. And then plus, if I do the same thing, if I isolate the sine omega dt from here and here, I'm left with a1 minus a2 times j sine omega dt. If I go ahead and say a1 and a2 are just constant, let me call it b1, and a1 minus a2 times j is this constant b2, my final solution for Vt for this underdamped case is e to the minus alpha t times b1, which is again just the constant, cosine omega dt plus this b2, again just a complex constant in this case, times sine omega dt. Lastly, let's go ahead and graph this function. So we have v of t with respect to time, where again, I'm going to consider that the initial voltage V0 minus across my capacitor is equated to 0. So it's 0 here. And this function is basically going to be oscillating, right, all the way, and it reaches 0 as t approaches infinity. Where again, here is t is equals to 0. If I go ahead and plot this decaying curve here and here, I'm going to get that this here is e to the minus t. And something to note is that from here to here is this period t, 2 pi over omega d. All right, so t is equated to 2 pi over omega d. And some things I can say about this case is that it has an oscillatory response, and some examples of a system that you can visualize that has an oscillatory response is something called a pendulum, right? Like the pendulum clock, right? It keeps going back and forth, back and forth. Another example is a bobblehead. And I think a bobblehead is more accurate because a bobblehead will oscillate and saturate to being in a stated position as time goes to infinity. Another example is a trampoline, right? If you jump on a trampoline, it keeps oscillating, and then as time goes to infinity, it saturates to 0. All right, in the next 2 videos, I'm going to be doing some examples of the source-free parallel RLC circuit, where depending on the circuit I pick, the case might be underdamped, critically damped, or overdamped. So make sure to look out for those videos. And if you have any questions or concerns about this video, please leave them down in the comment section below, and I'll be sure to get back to you. If you like the video, please give it a thumbs up, and please share the video to your colleagues and friends so they can also obtain the knowledge given in the video. And lastly, if you like the content the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.